Today we are going to talk about heat of fusion and heat of vaporization. Both relatively mean the same thing, but they occur at different times of a heating pathway. So let's talk about these guys. So if you remember, when we talk about specific heat, okay, it was energy needed to raise the temperature of 1 gram of substance by 1 degree Celsius. And we looked at the specific heat of this was water, remember, which was 4.184 joules per gram degree Celsius. Also, some other ones that you wouldn't hurt to know, this is for water. There's also the specific heat for water vapor, which is, where's it at? 2.02 joules per gram degree Celsius, and the CP of ice, which is 2.06 joules per gram degree Celsius. So it wouldn't hurt to remember all three, I'm sorry, of these numbers. But let's say like you're heating water to 100 degrees Celsius, so it's boiling temperature, okay? It doesn't actually boil right away, okay? Even though it might seem like it to your eye and what you're experiencing, when you actually heat water to a boil, it doesn't boil right away when it turns 100 degrees Celsius. So like, for example, like if you have boiled water, when it hit 100 degrees Celsius, not all the water all of a sudden just instantly vaporized and went to steam. That was false. It slowly actually vaporizes. Same thing when you see ice melt, right? You know ice melts at 32 degrees Celsius, I mean 32 degrees Fahrenheit or 0 degrees Celsius, but when it gets to that point, it doesn't automatically melt right away, right? Like if I go put ice outside when it's 33 degrees, 33 degrees outside in Fahrenheit, I don't put it out there and instantly, boom, it's water, okay? It's a process, and that's what we're going to be talking about now, is that when this energy is added to change phases or taken away. So we're going to talk about things called phase changes now too. So what I mean by that is that we're going to look at this curve, which is what we're going to call is basically a phase change diagram. Okay. What I mean by that, well, it's a version of phase change diagram, but what it shows is that on the x-axis you have heat being added. So this is heat being added as you go across. The y-axis is the temperature. So like for example, if this is the melting point, this would be 0 degrees Celsius. Boiling point of water would be 100 degrees Celsius. But what it's saying is, as, let's say for example, this is, I don't know, let's say negative 100 degrees Celsius. As you add more heat to, let's say, a solid piece of ice, right? The heat goes up, the temperature will slowly start to rise. Then, when it gets to this point, 0 degrees Celsius, as we've talked about, it doesn't automatically just go into a liquid phase. It's going to go through this process here. This process is what we'll call a phase change. Okay, this is what's occurring here is a phase change, right? Where you're adding heat because you're still moving to the right, but your temperature isn't changing because you're adding the heat necessary to actually change all of that amount that you have of, in this case, solid ice into liquid. Okay. So you don't actually have it go straight into a liquid phase. Like this all isn't one straight horizontal line. It goes straight up, plateaus, and straight up because you have these phase changes occurring at the plateaus now. And this is what we'll label them as the heats of. So in this case, this plateau, this phase change is the melting or the freezing point of, let's in this case, solid to liquid. So what this will be called is the heat of fusion in this case. And then at this point, okay, when it's the vaporizing one, we're going to call it heat of vaporization. But the important part is to realize that when it reaches that specific melting point, it doesn't automatically go into a liquid, right? It takes energy first. It takes in all the energy it actually needs to go all the way into a liquid. So at this point, this curve, this phase change, you might have half of it being water, half of it being ice. That's where you see the process of an ice cube, let's say, melting, right? You see it start to melt. That's where it's undergoing this phase change at this point. Okay. Same thing when you boil water. When you see the steam coming out, that's that phase change you see occurring, where you see some water still there, but you see some vapor actually coming out. But this is what we're going to talk about now, these two things, heat of vaporization and heat of fusion. So let's refresh them. Okay. When we talk again about heat of vaporization, okay, that's the necessary amount of energy needed to go from a liquid to a gas. Okay, so this is the energy needed for both of these. So to go from a liquid to a gas. And then heat of fusion is when I want to go from a solid to a liquid. Okay. So this will tell you basically how much energy is needed to go to that specific point. For example, where is it at? Let's say the heat of, and we'll call these delta H, okay? And if we're looking at heat of vaporization, it'll be delta H subscript VAP. So the delta H, let's say of water in this case, so water is 2,260 joules per gram. What that means is I need 2,260 joules of energy to vaporize 1 gram of water. So like if I had 10 grams of water, I would need 10 times this amount. And then for the heat of fusion, we're going to still label it delta H, but now instead of vaporization for VAP, we're going to put delta H of FUS, fusion. And the delta H of fusion for, in this case, where's it at? Of water of H2O again, is 334 joules per gram. So again, I need 334 joules of energy to melt 1 gram of ice. But this is what we looked at before, compared to specific heat, which if you guys remember was measured in joules per gram degrees Celsius. Because remember, there is no temperature change occurring at these points. They're staying constant. That's why you don't worry about temperature change like you do with specific heat. But let's look at this. Okay, just a really simple one first. If the delta H of vaporization of water is 226, 2,260 grams per joules per gram, how much water is required to vaporize, or how much energy is required to vaporize 45 grams of water? So I want to find the energy. So how you would use these ones is basically now you'd have Q equals the delta H of whatever you're looking at times the mass. Okay. In this case, I want to figure out how much energy is needed. I forgot that part in. So I want to find Q. So I have my delta H of fusion, which is 2,260 grams per joule, joules per gram, I'm sorry. And then my mass I'm looking at is 45 grams of water. So the amount of energy I need to essentially vaporize all of this water is going to be 101,700 joules. Okay, so that tells me I need that much energy to vaporize it. So you just take your heat of fusion or vaporization times your mass. That gives you your energy in joules. Let's look at another one, or how we can use both heat of vaporization or fusion and specific heat. Let's say, for example, how much energy in total is needed to change 12.7 grams of water at 23 degrees Celsius to steam at 159 degrees Celsius. So let me map this out for you guys so you can see what we're talking about. So here's 0 for temperature for water. Here's 100. Remember, it looks something like this. What we're saying is, I want to figure out, let's say we're starting, let's use black. Starting at 22 degrees Celsius. So I'm starting about here. And I want to get to 159 degrees Celsius. So I want to get to here approximately. And I want to figure out how much energy is needed to go from both points. Okay, so there's 3 calculations I'll actually be doing. Okay, I'll have to first figure out how to raise the water to 100 degrees Celsius. I then will have to vaporize it, and then I'll have to raise that steam to my temperature. So those 3 calculations we'll be doing. Right. So let's look at the first part of it. So if I want to first raise this 22 degrees Celsius of steam, okay, remember we're using Q equals mc delta T. Okay. So we want to figure out Q. We know my mass is 12.7 grams. Remember, specific heat of water is 4.184 joules per gram degree Celsius. Then my temperature change. Remember, I'm getting to first this point. Okay, I'm getting to this point, which is 100 degrees Celsius. So that's my final temperature. So I'll have 100 minus what I initially started with, 22, as my temperature change. Now I just gotta figure out what Q is when I do all that. So the amount of energy I need at this point is going to be 4,144.7 joules for the second part. Then, for the first part, I'm sorry, for the second part, now I'm going to go in that phase change. Okay, so now I am looking at the delta H of vaporization, which we just looked at previously, okay, which the delta H of vaporization for water in this case, remember, is 2,260 joules per gram. So I want to figure out how much energy is needed to vaporize this amount of water. So remember, you'll take your heat of vaporization times the mass. Let me box this up so we know that's our first number real quick. So we've got to multiply these two. And the amount of energy needs to vaporize 12.7 grams of water is 28,702 joules. So I have part 1, I have part 2. Now I am at 100 degrees Celsius. It's all steam. Now I just have to raise this steam from 100 degrees to 159 degrees Celsius. So again, I'm going to go back to Q equals mCp delta T. My mass still has not changed because it's still the 12.7. My specific heat now is specific heat of steam, which was given to me. And now my temperature change, the final I want to get to is the 159. So this will always be a positive number too, guys. It should be right now. Minus 100 now because you started 100. That's where you're ending at this point. And then you'll figure out Q. So you should get approximately 1,513.6 joules. And now I just have to add up all 3 of my box numbers to find my total energy. So to find the Q total, I'll take 4,144.7 joules, 1,513.6 joules. Oh, sorry, that should be a plus there. Plus 28,702 joules. So my Q total is going to be a lot of energy. 34,360.3 joules. Okay. So there's a lot of multiple parts to this. But I like to draw it out first, usually when I first get in the hang of it. So at this point, I would like to draw it out like at this right here. So you understand that you first have to raise the water to boiling point, which we did here. Then you have to undergo the phase change from water to steam, which we did here. Then we get to steam, we have to raise it to our 159 degrees Celsius, which we did here. All right, I am actually, so what I'll do at this point is, this will be a little longer video because it took a little bit longer to do, is if you think you understand it, you're good to go, okay? The homework is SP 6, all right, if you want to go ahead. But if you are still wanting to do another one example like this, I'll keep going with this video. It'll be a little bit longer than normal. This might take another 3 or 5 minutes to do. But I will do this next one and we'll be done basically. So you have the choice of either leaving or staying on. But now I want to figure out how much heat energy is needed to require a change of temperature of 125 grams of ice to from negative 32.9 degrees Celsius to liquid water at 75. So again, we're going to look at my little handy dandy graph. This was 0. This was 100. So now I am essentially at this point and I want to get to this point. So total energy from those 2 points, I'll put Q total. So again, I have to go from this part 1, this part 2, and this one 3. So I have 3 calculations to do again. So let's figure out the first one. We have to raise the ice to melting point. So we have to figure out the Q of this portion, number 1. I'll put Q1 just to make sure. So Q at point 1, we know our mass is 125 grams. Specific heat of ice is 2.06 joules per gram degree Celsius. And my temperature change now is going to be 0 minus negative 32.9. Remember I said this should always be positive, which it will be when you subtract 0 from negative there. So the Q to raise the ice to 0 degrees Celsius should be approximately 8,471.8 joules. Okay, so that's my first Q. Now I'm at 0 degrees. Now I can melt it. Okay, so now I have to use Q equals the heat of fusion in this case times the mass. And the heat of fusion of water, if you guys remember, was 334 joules per gram degree Celsius, and I have 125 I'm trying to melt. So my energy needed to melt that amount of ice is going to be 41,750 joules. Okay, so here's Q2. And then the last part, we have to raise that water now to 75 degrees Celsius. So we'll use Q equals MC delta T, Cp. So Q for 3, my mass still hasn't changed. Specific heat of water, 4.184. And now I'm going to 75 degrees Celsius, and I started at 0 degrees Celsius. So again, just gotta multiply all those numbers through. And this one you should get 39,196.8 joules. So we have all my Q's. I just got to add them all up to figure out the total energy. So 8,471.8 plus 41,750 plus 39,196.8. And the total energy needed is going to be 89,418.6 joules. And there we go. All right, like I said, homework is SP6, so you guys can go ahead and get that going.